Hello and welcome to lesson 3 of week 10. In this lesson, we are going to talk about self-balancing search tree. My name is Mildred. An AVL tree is self-balancing binary search tree where the difference between the heights of the left and the right subtree, that height is the balance factor. When the tree is balanced, then we have a minimum tree height, and when we have a minimum tree height, it makes operations faster. So why do we need to balance? If in a normal binary search tree, elements are sorted or inserted in sorted order, the tree is going to be skewed, right? And so this will now act like a linked list with big O of n search, insertion and deletion and time. But AVL tree will address this issue by performing the rotations to maintain balance. So the performance will now be big O of log n for all operations, which is significantly faster than when the tree is out of balance. So when we want to get the balance factor, called that BF, we want to get the height of the left subtree minus the height of the right subtree. So if the balance factor is -1, 0 or +1, the tree is balanced. If it's less than -1 or greater than 1, rotation is needed. Now where is that rotation needed? If it's 0, the node is balanced. If it's greater than 0, we have it right heavy, and if it's less than 0, we have it left heavy, and so it will tell us where we want the rotation. And so when we have a balance factor that violates, we have one of 4 rotations which is required. Either we do a left rotation, a right rotation, we do a left right rotation, or we do a right left rotation. So let's look at how we can implement an AVL tree in Python. So let's create a node class. So I'll say class node, and we will create the init method, and for this init method we want to supply the key. Now we want to create other properties that will be defined by other methods. So we'll say self.key is equal to key, and then we say the self.left, we'll just set them to none. We set the right, self.right, we'll set it to none, and then we'll say self.height, we'll set the height to 1, and this height of 1 is what we'll use for balancing. Now let's create a helper function that we'll use to get the height and get the balance of this tree. So let's create a let's call this get height method, and we want to just supply the node, and so we'll get the height of it. So say if not node, so if there's no node, we want to just return 0, and if there is, we want to return the node dot height, because we set the height to default of 1. Right now we want to get balance, balance, and for balance we know what the balance factor is. We want to get the height of the left subtree minus the height of the right subtree, and when we get this, when it's 0, when it's 1, when it's less than 1, we know where it is, whether right or left heavy, and we'll know whether it's balanced or out of balance. So we'll say def get balance, and we want to pass in the node, and here we'll say if not node, we want to return 0, and if not, we'll return get height. We'll get the height of the left node, node.left, and minus get height right, like that. So we have these helper functions. Now let's think of the rotations. So when we have this and we know whether it is left heavy or right heavy, we will know whether we want to rotate left or rotate right. So let's create a method that we'll use to rotate right, and let's create a method that we'll use to rotate left, and then now do a method that we use to insert, and we'll insert it in the balanced fashion. So let's say def, let's start with right. So let's say def right rotate. Before we rotate right, we'll always check the balance factor, but we'll do that in the insert method or another method. But for here, let's just say it will look at, let's say x is equal to y dot left, and then we'll say, let's call this t2. I'll call it t2 like this. I'll make it equal to x dot right. Now I want to perform the rotation here. We set the value of x and t2. Now the right of x is going to be equal to y, and then the left of y is going to be t2 for rotation. So perform rotation to say x dot right is equal to y, and y dot left is equal to t2. So we rotated that. Now when this is rotated, let's update the height. So we'll say y dot height is now equal to, so to get that height, we'll say 1 plus the max of get height. We use our helper method, and we're getting the height of left. We're getting the height of left, and then we're getting the height of right, and then we'll get the x dot height is equal to 1 plus the maximum of the height of the left and the height of the right. So we'll just use x for here. Let me copy this and I'll paste it here. I'll say x dot left, x dot right. Now at the end of it we'll return x. So we're returning x at the end because we supplied y, and we rotate and return x. Now for left rotation, it is going to be y will be x dot left and t2 will be y dot left. We're just rotating the other way, and then we'll have instead of having x dot right, we'll have y dot left is equal to x and this. I'll copy this. Let's just make it faster because it's similar. Just let's see how we can make this. So here is left rotate, and for left rotate we supply x and we'll say y is equal to, so this will be y is equal to x dot right, and this will be x is equal to, so this will be equal to t2 is equal to y dot left. So we're changing it. Now when we have x dot right here, we'll change this to t2, and y dot left here, we'll change this to x. Now for this y dot height, 1 plus, so we have y dot height is equal to 1 plus max get height, y dot left get height, y dot right. I think the definition is still the same. Y dot height is, so this will be x dot height, I think, and this will be y dot height. So the x dot height is here will be x. Oh, would have left it the way it was. It would have worked out fine. And x dot right, and then we'll change this one to y. So we'd have left it the way it was and just change that to yx. Okay, so we can leave it the way it was and change here to y, here to x, and here we are going to be returning y. All right, so now we've seen how we do this rotation. If you don't get a full understanding, you attend the LifeWave conference where we'll try to build an app for us to illustrate it better, and you'll see the implementation of this problem. Now we want to insert this with balancing involved. So we did the insert method in the previous lesson, but in this lesson we want to make sure when we're inserting, we are balancing the tree while inserting. So we'll say def insert root. So let's do the normal binary search tree insertion. If not root, we return node key and created a node class, and then L if key is less than root dot key root dot left equal to insert root dot left key, and else root dot right is equal to insert root dot right key. Okay, and we always update the height, and here we'll update the height to say root dot height will now be 1 plus the mark of get height, and root dot left get height root dot right, and then let's balance the tree. So let's say here we'll get the balance factor first to see if it's out of balance. So we'll say balance is equal to get balance, and we want to get the balance root, and then we'll apply rotations. If the case is 1, so if the balance is greater than 1 and the key is less than the left side key, return the right rotate, and if the balance is less than -1, we do the left rotate. And if the balance is greater than 1 and the key is greater than the key of the left, then we are going to set the left root to left rotate, and then we'll return the right rotate of the root. And then case 4 is when we have the balance -1 and the key less than the key of the right root, so something like that. So it's, you have to go to your lesson resource, read the definition, understand the definition, and then it will be easy to apply based on different cases. So the first case is when we want to do a left rotation. So we'll say for this case, if the balance is greater than 1 and the key is less than the left key, then we want to return right rotate, and we'll right rotate the root. Now the second case is if the balance is less than -1 and the key is greater than root dot right dot key, we want to return left rotate root. So we have the left case, we have the right case, and then the third case we want to look at now is left right case. So this will be if the balance is greater than 1 and the key is greater than root dot left dot key, then we will do the left root will now be equal to left rotate root dot left, and the return will be the right rotate of the root, return right rotate root. Now the fourth case is right left. So it's the same thing, but this time it's less than -1. So say if balance is less than -1 and the key is less than root dot right dot key, we want to now set the root right will be equal to right rotate root dot right, and we return left rotate root, and at the end of this all we want to return the root. Now let's create a traversal method just for us to use to display at the end. Let's say there, let's just do a pre-order traversal, pre-order root, and for this we are going to do the root first. So print, so let's say if root, just check condition, if root, then we print root dot key, and let's put a space at the end is equal to space, and then we'll do the left reorder root dot left and reorder root dot right. And now we can test this and see. So let's test it and see. If name root is none, key is equal to, let's put all the keys we have, let's put let's say 10 20, 30, 40, 50, 25. And let's insert this when we loop. So let's say for key, in keys, we want to say root is equal to insert root key. And print here now. Let's print order. So let's see if this works. So let's see method def insert. So we have def insert. So the issue here is this is not part of the class. It's not a class definition from here. These are all outside the class, and so I'll take it out. That's the error, sorry. And so they're not part of the class definition. So I'll clear here and I'll run again, and cannot access local variable y where it is not associated with a value. Let's go back there. We have the y first here. That's the mistake. So we have 30, 20, 10, 25, 40, 50, none. So we have this inserted and it's balanced because the order we have here is 10, 20, 30, 40, 50, 25. So all of these that are sorted is going to be skewed and it will be out of balance, and so it rebalanced the tree, changing the roots and the left and the right placements, so the tree will be balanced. So this is an example of balanced tree, and in our live web conference we are going to do labs of real-world applications that will enable us to understand everything that we have discussed this week better. Thank you and see you next week.